I love the internet. Facebook, Instagram, there's just so much fun stuff on there. And I came across this and I'm like, yeah, I think that's how a lot of my students think. How I see math word problems. If you have 4 pencils and I have 7 apples, how many pancakes will fit on the roof? Purple, because aliens don't wear hats. That makes absolutely no sense, right? Absolutely no sense. And sadly, word problems make very little sense to a lot of people. Okay, I've decided that there's 2 kinds of people in the world. People who understand and like word problems. We called them story problems when I was growing up. Maybe that makes them sound friendlier, I don't know. People that just get story problems. I think story problems are fun. And then there's a group of people that word problems is just like this. Like, how on earth, okay? If you see word problems like this picture, that doesn't mean you're stupid, okay? It just means that your brain works differently than my brain. And that's not necessarily a bad thing. For solving some chemistry problems, it's going to make it harder for you. But for your overall value as a human being, that has no bearing at all. I think a lot of people's problems with word problems is that you were never really taught how to do them. I watch my kids come through and they keep changing the curriculum and stuff, and I'm watching what they're doing as they come along through elementary school, and I'm thinking, I don't know. I can kind of see why some of my college students, you guys have graduated from high school, but somewhere along the line, the system has failed you, and you just didn't understand how to do this. I had a friend about the same age, this was a few years ago, and she was going back to school because she wanted to become a teacher. And she had to take algebra, and she was very math phobic. She's like, oh, I can't do math, I'm horrible at math. But she wanted to get her teaching credential, and so she had to take algebra. So she started algebra at the community college and realized a couple weeks in, and she dropped it. But they had a late start class taught by a rather unorthodox guy, but he had a knack for teaching people algebra. And she had to work at it in that class, but she finally understood it. And she was so excited. She's like, oh, I see it now. I see how all this number stuff works. And she was not a bad student in high school. She did well in high school, struggled in math, but somehow got through anyway, but never understood what she was doing. So I suspect that there's a good number of you that are in that position. You managed to pass whatever math requirements they made of you in high school, but you're not really understanding, especially when it comes to word problems. They look like this. I can help you with that, okay? But it's not just, I can't just give you a pill that's going to make you understand them. You're going to have to work at it, and you're going to have to ask a lot of questions. Because if you don't ask questions, then I have to assume that I've got a very unusual class where everyone gets story problems. I don't think I guess if you got a bunch of math majors or something, maybe you could, but you can't just really gather a group of people and have all of them be the story problem kind of people. So I'm just saying that to say I know some of you are coming from a place where word problems are difficult, and I am very willing to work with you. I will work as hard as you work. And I can help you figure these out. And the thing is, to be truly successful in chemistry, you have to figure out word problems. Because the math we do in chemistry is not anything crazy. We're not going to do calculus or anything. We're going to use basic algebra. Basic algebra. We don't even do quadratic equations or anything crazy like that. Just basic algebra. A little bit of simple geometry. The thing is, it's all applied. And so it ends up being a lot of word problems. We took 2 grams of this, and we did this to it and that to it, and then you have to write it out in an equation. So we're going to work on how to solve word problems. So getting to the equation from the problem statement is usually the hard part. Once you get the equation written out, you're good. You learn how to do that. It's taking the words and translating them into an equation. And that requires critical thinking. And there's no simple formula that I can say, well, do this and this and this, and voila, everything's going to work every time. You have to be able to think about it and understand it. You can learn problem-solving strategies. One thing we're going to learn is how to convert units. And many of the problems that we do in chemistry can be thought of as a unit conversion problem. Then there are other problems that require the use of a particular equation. Students generally have less trouble with those. Oh, there's an equation. Okay, I can identify this and this. I'll stick it in the equation. Good. It's the ones that there is no specific equation for that tend to give people trouble. So we need to learn how to convert between units. You can think of a unit as being like a variable in algebra. Those pesky little letters, and they're multiplying and dividing, canceling out x's and y's and a's and b's. The units can be treated or thought of that way because units multiply and divide, and they can cancel out. So the volume of a block of wood we were talking about, 1 meter times 1 meter times 1 meter. What do you do with the meters? Do you say the volume is 1 meter? No, those m's, those meters multiply and you get m cubed. Just like if you took x times x times x, it would be x cubed, x to the third power. Units can cancel out as well. So we're going to use units as a guide to solve problems. And when we do this, it's called dimensional analysis. The units are like the dimensions, and analysis is analyzing. Dimensional analysis. I learned dimensional analysis as a junior in high school in physics class. I would say that's probably the most valuable thing I learned in all of high school, was how to do crazy things with units. So my teacher showed us that in physics, if you can get the units to work out, you can usually solve the problem even if you forgot what the equation was. And it was just a beautiful, beautiful thing. So I'm going to teach you dimensional analysis. And dimensional analysis does have application to your everyday life. Say you've got a garden and you want to put some manure on it, and you want it to be, 4 inches deep. So you go out and you measure the garden, and it's 10 feet by 12 feet. And then you go to the garden center, and it's sold in cubic yards. What do? You've got 10 feet by 12 feet by 4 inches, and you need to convert that into cubic yards. Dimensional analysis can let you do that easily. Dosing a child with ibuprofen, or dosing a steer with a medicine. Here's an example. We have cats. Cats get fleas, so you get the Advantage flea stuff and you put it on their back. The companies that sell that sell it for cats and for small dogs and for large dogs, and it's 3 months' supply for one animal in a package. But it's the same chemical for the 55-plus pound dog or for the 9-pound cat. And the cost of that package for the big dog is only a little bit more than for the little cat. So if you understand how to deal with units, you can look on the package, thank you regulations that require all that labeling, figure out how much of that active ingredient is in the dose for the small cat. You buy the big dog one and a little syringe, you do a little calculation, and you calculate that you need, I think it was like 0.5 milliliter of the big dog one to put on the cat. Done it many times, haven't killed a cat yet. No animals were harmed. But you can do those calculations. It comes in really, really handy sometimes. So dimensional analysis, really important. Here are some things that we need to keep in mind. Always write every number with its associated unit. They go together. Don't just write the number down. Even if it's just in the middle where you're showing your work. Write the unit every single time. Yes, it's annoying, but getting the answer wrong is a lot more annoying. Taking a second to write the unit or not following that advice, getting enough answers wrong that you fail the class and have to take it over again. That's even more annoying. Always include the units. So in your calculations, the units have to be in there. Do not let units magically appear or disappear. Treat them like variables. So you're doing a calculation and you know the answer is supposed to be in cubic centimeters. Don't just take the numbers they gave you and multiply them and just magically put the correct unit on the end. It's probably not correct. You have to look at the units, and sometimes you have to convert them into other units and work with them. So for most conversion problems, we're given a quantity with one unit, and we're asked to convert that quantity to another unit. And those are going to take this form. We've got some information that's given, and then we're going to apply a conversion factor, and we're going to end up with the answer that we need. So let's just do a very simple example here. How many feet, what am I writing? I don't know what I'm writing. How many feet are in 37 yards? So they're giving us some information and they're asking for information. They're giving us 37 yards. What are they asking us for? Feet. So the general pattern here is that we start with what's given. So we've got 37 feet. And we're going to apply a conversion factor that relates feet to yards. And we're going to end up with yards, which is what they're asking us for. Thank you. My husband calls that a brain fart. I did that to test you, to see if you're paying attention. No, I just screwed up. 37 yards, how many feet? Thank you. Okay. So to do this, we need to know the relationship between feet and yards. How many feet are in a yard? 3. So do we want to multiply by 3 feet or divide by 3 feet? Well, we want to multiply, but that's where it's hard. Do we multiply? Do we divide? That's where dimensional analysis comes in. We're going to look at the units, and the units will tell us what to do. So if we think of this as, if we think of the units as variables in algebra, we want to get rid of yard. So if we divide by yards, a yard divided by a yard is 1. Anything divided by itself is 1. So we say those cancel out. We want to end up with a unit of feet. So we need to multiply by that unit. We're multiplying by the desired unit. We're dividing by the given unit. We want the units to cancel out. Dimensional analysis, you look at the units first, and then you deal with the numbers. So we put the units in there, and then we say, well, what's the relationship? How many feet, how many yards? Oh, well, it's 3 feet in 1 yard. It would be silly to say 1 foot is 3 yards, right? That's where it's helpful to have a clue about how big these things are, so that you can recognize if you're being silly. Oh, I probably should have chosen something that I could do in my head, but 37 times 3. 111. It's kind of a nice number. 111 feet. that answer is not paying attention to significant figures. Let's practice our significant figures. 37 yards, is that an exact number? No. It's a whole number, but it's not exact. That's a measurement, so there's uncertainty in the 7. So that has 2 significant figures. How about 3 feet per yard? Is that exact? That's exact. A yard is defined as 3 feet. So the 3 and the 1 there are exact numbers. We could say they have an infinite number of significant figures, which means that we can ignore them in terms of figuring out significant figures. So if 37 has 2 significant figures and we don't have to worry about the conversion factor, how many significant figures should our answer have? 2. So should we round that to 11 feet? No. Because how could 37 yards be the same as 11 feet? That's silly. Scientific notation. So 111 is 1.11 times 10 to the 2 feet. So we can round that then and say that is 1.1 times 10 to the 2 feet. What we're saying is 110, where this is where the uncertainty lies. But that's an ambiguous way of writing it, and so I'm not going to promote that. Any questions? Where do these conversion factors come from? Conversion factors can be between any 2 quantities that we know are equivalent. And so this is table 2.3 from your textbook. It's a very useful table. So this is giving us, 1 kilometer is 0.6214 miles, giving us the relationship between meters and inches and feet and centimeters, inches and centimeters. They're going to kind of assume that you know the relationships between the English units. They're not going to give those to you in this table. On an exam, I would only assume the very, very basic ones. I would assume that you know that there are 12 inches in a foot and 3 feet in a yard. I would not assume that you knew how many feet or yards were in a mile. It's kind of an odd one. So conversion factors like this, you don't need to memorize. There is one on here that I'm not going to require you to memorize it, but I think you should. And that's this guy right here. 1 inch is 2.54 centimeters. We end up using that quite a bit, so that's a good one to memorize. Now notice that this says exact. So in general, units where, conversion factors where 1 unit is in the metric system and 1 is in the English system, in general, those are not exact. So in this guy, what we're thinking is exactly 1 kilometer is equal to 0.6214 miles. That has 4 significant figures. There's uncertainty in the 4. We're going to assume that the 1 is exact, but the other number is not. The exception to that is between inches and centimeters. So they actually redefine the inch as being exactly 2.54 centimeters. So that one's exact. So those are length conversion factors. Here's mass conversion factors and volume conversion factors. So there's 2 basic ways that you find conversion factors. You go look in a table like this, or you may create them using the metric prefixes. The metric prefixes are not going to be given to you on an exam. You're supposed to memorize those. You need to memorize them for the memorization quiz, and I'll be giving you a memorization quiz next Tuesday, and on Thursday, and the following Tuesday. So you need to memorize those. So let's practice constructing some conversion factors. What's a conversion factor relating feet and inches? Yeah, 1 foot is 12 inches. So we can write them like this. Oh, I don't want to be red. Let's be yellow for a change. 1 foot equals 12 inches. So that's what some books call an equivalence statement. That's what you see in the table of conversion factors, the relationships. We can make 2 factors for our equation out of that. So let's just see how that works. What if I divide this side by 1 foot and I divide this side by 1 foot? Are those 2 things still equal? They are. So a little math refresher. If you have an equation, an equality, one thing is equal to another thing. If you do the same thing to both sides, they're still equal. Just like a teeter-totter. You've got some people sitting on each side of the teeter-totter. And you give this person an 8-pound bowling ball and that person an 8-pound bowling ball. If they were balanced before, they're still balanced. You've got more on each side, but it's still balanced. So we can do the same thing to both sides. We can divide each side by a foot and it's still the same. What is 1 foot divided by 1 foot? It's 1. Foot over foot cancels out. 1 over 1 cancels out. That is equal to 1. When we multiply something by 1, do we change it? No. So when we do something, and that's what this dimensional analysis is all about. If we say, okay, well, so-and-so is 6 feet tall, how many inches is that? And we multiply by this conversion factor that we just made, 12 inches per 1 foot. This conversion factor is equal to 1 because 12 inches equals 1 foot. It's the same length. Yes, the numbers are different, but the units are also different. 12 inches and 1 foot represent exactly the same thing. So when we multiply by 12 inches over 1 foot, we are not changing the value of the quantity. We are just changing the unit. So what is that? 72. So that equals 72 inches. All the conversion factors are going to do that. Essentially, we're multiplying by 1. We're just multiplying by 1, and that looks really, really, really weird. Okay, this one is one I told you is a good idea to memorize. Does anybody remember it? Inches and centimeters? 2.54 what? Centimeters equals 1 inch. So from an equality like that, we can make 2 conversion factors. We can say 1 inch over 2.54 centimeters, or 2.54 centimeters over 1 inch. Any questions? This is critical stuff, understanding this. We're going to do something later called stoichiometry, where we're going to convert between grams of one substance to moles of that substance to moles of a different substance to grams of of that second substance. And that's a very important part of chemistry. And if we learn how to do dimensional analysis, that is pretty simple to do stoichiometry. So I always have some students, well, I know how to convert units. I don't need to learn this new technique. I just know how to do it. Well, yeah, you know how to do it with units that you're familiar with. But when we get to grams and moles, you're going to get confused. And so that's why I really, really want you to learn dimensional analysis. I don't know about you, but I think we need a little break here. So let's take a break.